Hereby I open this academic ceremony in which Mr. Hongxing Luo will defend his academic thesis entitled Heart Sounds from Animal to Patient and Mhealth. May I invite you to present a summary of your study and the conclusions of your thesis in the next 50 minutes. I'd like to give you the word.
Thank you, Prorector. Dear Prorector, dear committee members, dear family, dear friends, colleagues, good morning. In the upcoming 15 minutes, I would like to present a summary and the main findings of my dissertation titled Heart Sounds from Animal to Patient and Mhealth. At this special moment, I would like to share with you my feelings in the following audio, so please listen carefully. Maybe you are already familiar with these sounds, especially when you feel nervous or at night when the environment is very quiet. But in the latter case, if you hear your heart sounds, maybe you need to go to the hospital and have the doctors to check your heart to see whether anything is wrong. But since these sounds are from a beating heart, we call it simply heart sounds. And you can listen to the sounds, you can also see the sounds by, for example, you can print them on the paper, and then you can see this kind of signals. And in these signals, the first impression is that the heart sounds are regular. So here you can see they occur at a given timing interval. And then if you look into the heart sounds in more details, you can classify them into two categories, either the first heart sound or the second heart sound. As you can see, the first heart sound has a longer duration. In comparison, the second heart sound has a shorter duration. And they occur regularly in the orders of S1, S2, S1, S2, S1, S2. Of course, the S1 is called the first heart sound, and S2, the second heart sounds. And then the next question that goes to your mind may be, where do these sounds come from? And then if you look at the position of the heart in the human beings, it is located inside of the thorax. And the heart is actually an engine that receives blood and pumps blood to the bodies so that you can get enough nutrition and oxygen. So the heart pumps day and night. And by looking at this figure, you may already be able to hear the sounds, dum-dum, dum-dum, dum-dum. So the first sound that we call S1 occurs during contraction of the heart, whereas later on, as the contraction approaches the end, relaxation occurs. So S2 is the result of relaxation of the heart. Of course, just like when I'm speaking, you can understand that heart sounds are speech of the heart. So the next question is, how can we decipher this kind of mysterious speech of the heart? So here in this presentation, I'm going to talk about heart sound splitting in animal studies. We are also going to look into heart sound-derived systolic intervals in both animal and human studies. And then in human studies, we are also going to address a very important issue, which is heart sound frequency, amplitude, and timing in the patients with heart failure with preserved ejection fraction. And finally, in order to translate our findings into the reality, we investigated the measurement of heart sounds using the smartphone here, as you can see. Let's start by heart sound splitting. If we look at the heart, actually you can easily find out that the heart is divided by the septum in the middle into the left ventricle and the right ventricle. So you may imagine that the two ventricles contract together, but they do not contract exactly at the same time, giving rise to the dysynchrony of the two ventricles. But how does it relate to heart sounds? If we look at heart sounds, since S1 occurs during contraction and S2 occurs during relaxation, you can easily hypothesize that S1, for each of S1 and S2, they should contain one component from the left side of the heart, while the other component from the right side of the heart. So as you can see, S1 should contain two internal components. So it's the case for the S2. We call this as splitting of the heart sounds. We investigate this in animal studies. We perform animal studies in pigs, and then we collected pressure tracings and also heart sounds during our animal experiments. From pressure tracings, we calculated the synchrony index, and from heart sounds, we calculate the splitting interval. As you can see, there is a positive correlation between heart sound splitting and interventricular dysynchrony. This means that we can use the simple heart sound measurements to evaluate the interventricular dysynchrony, which is usually very difficult to be assessed. And then let's take one step further by adding the electrical signals of the heart into our whole picture. So here on the left side, you can see the ECG, which is electrocardiogram. It is one of the most common ways to record the electrical signals of the heart in hospital. On the right side, you can see a synchronous recording of ECG and heart sounds. And from the synchronous recording, we can measure some timing intervals, such as VS1, the time interval from the electrical impulse of the ECG to the occurrence of S1, or the intervals between the onsets of S1 and S2. Both VS1 and S1, S2 can be classified into the systolic time intervals because both indexes are related to systolic of the heart. I think these concepts are a little bit difficult to be interpreted, so let's just use some daily examples to better understand them. So for VS1, imagine that in a sprint, the commander holds a pistol, so he is the V. And the runners, they are called S1. So for the runners, as long as they hear the sounds from the pistol, they quickly rise and start up. Of course, the faster they can react to the sounds of the pistol, the better their results will be. So it's the case for the VS1. So for VS1, the shorter it is, the better the heart performs. It means that the heart has a better reaction to the electrical impulses. What about VS1, S2? What about S1, S2? So S1, S2 is the time interval for contraction of the heart. You can also imagine that as we water the flowers, we squeeze the bottle so that the water can come out of the bottle into the plants. So in this case, we can compare our hands and bottles into the heart, and the water inside the bottle as blood. As the heart squeezes the blood, the human peripheral organs, including brain, hands, they are nutritioned. So as you can imagine, the longer that we contract the bottle, the more blood will be supplied to the body. So the longer the S1, S2 interval is, the better it will be for the human beings. To investigate this hypothesis, we performed both animal and human studies. So in the studies, we changed the pacing settings using the pacemaker. And then we measured the VS1 and S1, S2. And then as you can see, as we changed the pacing settings, the VS1 gradually decreased, and then it increased. But for S1, S2, the trend is the opposite. But here, you can see a lot of noises in the data. In order to reduce the noises of the data, we use a curve-fitting method so that we can more exactly identify the best position for the heart performance. As we assumed in our previous slides, the best heart performance should be at the shortest VS1 and the longest S1, S2. So that is the case in our study. We assess the heart performance using LVP max, LVDPDD max, and stroke work. However, the next question is, even though these indicators are may work for heart failures, in recent years, there is a phenotype of heart failure which is drawing increasing research interests. This phenotype of heart failure is called HFpEF, or heart failure with preserved ejection fraction. So for these patients, as you water the flower, the bottle can never rebound again. And when these patients go to hospital, they are evaluated by ultrasound. Among all the indexes, one of the most important one is called E/E prime. But ultrasound examination takes time. It takes around 30 minutes. And then we are wondering whether we can use the simple heart sound measurements to evaluate these patients. So we recorded heart sounds from these patients, and then we calculated 16 heart sound features, including amplitude, frequency, occurrence, and timing of heart sounds. And then we select 4 features which were related to the diagnosis of HFpEF in these patients. So they are the frequency of the first heart sound, the interval from the QRS onset to the S1 onset, and the interval from the QRS onset to the S2 onset, corrected for RR interval, and the percentage occurrence of S4. And from our discussion, from our results above, you may think that, okay, now maybe we are able to use heart sounds as a useful marker of heart failure in these patients. However, if we consider the reality, we perform these studies in hospital or in lab. But for our patients, they spend most of their time at home. So the question is, how can we approach these patients? Or more exactly, how can we measure heart sounds from these patients? And then if we look at this, and then we use this to call others. And then the idea is whether we can use also the smartphone to record the subtle heart sounds. So the heart sounds may not be heard by our ears, but may be easily captured by smartphone. So our research question is, can smartphone be used as stethoscope? In order to test the idea, we developed the Echoes app. So the users put the app on the chest so that they can measure heart sounds. And then the heart sound signals will be uploaded to the cloud. Within a few months, we have over 1,100 users who contributed to around 7,600 recordings. We looked into the quality of these recordings and found that around 80% of the users were able to make a good quality heart sound recording. And overall, around 75% of the recordings can be used for further signal processing in order to get features relevant to medical purposes. We take a step further by looking at the factors affecting the heart sound qualities in these users. As you can see, different versions of iPhone or smartphone did not affect the heart sound recording, neither sex. However, for the people of more advanced age, they did have some difficulties in recording heart sounds. For BMI, it did not affect the quality of heart sounds. And so, if you think about this app and this application, the question is, why should I investigate this? Why should I turn a smartphone into a stethoscope? As we review the history of heart sound research, we can draw on the conclusion that for heart sounds, new tools always bring new areas of research. So heart sound has a history of around 200 years. And if you look at this wave in more details, you can divide it into 3 phases. So we have 3 waves of heart sound research. And each wave is driven by different factors. The first wave is driven by the PCG machine, and the second wave by signal processing, and the third by open access heart sound dataset. If we only look at the tools for measurement of heart sounds, we can see that the tools have evolved from the primitive stethoscope to the phonocardiogram machine, and to more recently, portable, implantable, and wearable devices. And overall, the trend is that heart sounds are making its way from hospital into home purposes. And we hope that smartphone can be one of the cheapest solutions among them. Here comes to our conclusion. So in our journey of deciphering speech of the heart, we look at heart sound splitting in animal experiments. In combined animal experiments and human studies, we look at the systolic time intervals. And we use them as the indicator of myocardial contractility. And in human study, we also look at a special disease called HFpEF and identify 4 key features related to the disease. And finally, we explore the feasibility of using smartphone to record heart sounds as a large-scale solution for heart sound measurements. Thank you very much for your attention. Now I would like to give the floor back to the pro-rector.
Thank you very much, Mr. Luo. And due to time, since we're a little bit over time, I would like to swiftly start the discussion. For the audience, we have 7 members in the corona, and there is 1 member online, but you will notice this yourself. The opposition will be then opened, basically by Professor Lumens. He has his affiliation is with computational cardiology, and I would like to give him the first word.
Thank you, Pro-Rector. Dear candidate, let me start with congratulating you with all this work and with you, your supervisory team as well. You cover a lot of fields.
Yeah.
I mean, you use this technology for diagnostic purposes, screening,
Yeah.
you suggest, optimization. So now I'm giving you $250,000 as an investor to start up a company,
Yeah.
and you have to choose where to invest in. What will you do and why?
Yeah. Highly esteemed opponent, thank you very much for your question. If I had a chance to start a company, I have to think carefully about my direction in the future, of course. I think the most promising direction may be for remote home monitoring. Because nowadays in the hospital, we already have quite some ways or quite some tools, such as ultrasound or MRI or CT, to evaluate the patients, especially the heart. We can also use the modeling, computation modeling, to access the cardiac function. Heart sounds is just a very simple tool. As you can see, we can measure that just within a few seconds, and then we can note whether your heart is healthy or not. So I think it is easy to use for the patients. And also, with the development of the internet, with the widespread use of the smartphone in the past decades, we can easily reach millions of users in a very short time at a very cheap cost. And that is very friendly to a startup company. So if I have a chance to test, of course, I would like to further my research and to build an app for more users.
So you're leaning towards the Mhealth side of the spectrum that you investigated?
Yes.
Okay, thank you. I would like to dive into chapter 2 with you. So you focused on the second heart sound as a measure of interventricular electromechanical desynchrony.
Yeah.
I was puzzled. So can you explain to me why you looked at S2 rather than S1? And, well, give your arguments, please.
Yes. And highly esteemed opponent, thank you very much for your question. Yes, indeed, we looked into S1 splitting at the very beginning, but we failed. And in animal experiments and also in the soccer study, in human studies, as you can see in the chapter of the systolic time intervals, we look at the S1 splitting. I think there are a few reasons for this. If you think about the S2, because the RV ejection time is longer, so the separation between A2 and P2 is supposed to be much longer than the time interval of the M1 and T1. So because the time interval for S2, the splitting interval is longer, so we can easily detect that. The second reason is that if you look at the time frequency spectrum of the heart sounds, for S2, you can always identify the ridges, as I said in this chapter. But for S1, that is not the case. For S1, if you look at the time frequency components, they're more like two clouds of signals. So they're round. So it's very difficult to identify them. Also because the frequencies of the two components are very close. So it is very challenging.
Okay, but may I argue that S2 and the splitting thereof may also be confounded by other properties of the heart, not necessarily relating to the electrical dysynchrony? How do you think about that? Yes, indeed, that is likely. And that is why we do research in heart sounds. We think it is very complex. And as for S2 splitting, a key confounding factor is relaxation, interventricular relaxation. It is not only about the contraction of the heart. Of course, S2 occurs at the end of the contraction. That is why we investigated the contraction using S2 here. And of course, relaxation may also play a role here. Mm-hmm. Yes, and also because heart sound is driven by the pressure difference. So we also need to think about whether pressure difference plays a role here. Okay, thank you for your answers. With that, I would like to give the word back to the prorector. Thank you.
Thank you very much. The opposition will be continued by Professor De Hooger. It will be online, the only online opposition. Professor De Hooger is affiliated in the Department of Cardiovascular Imaging and Dynamics, and I would like to thank him that he joins us from Leuven University in Belgium. I'd like to give you the word.
Thank you, Prorector. First of all, I would like to apologize for not being there physically, but unfortunately I couldn't make it all fit in my agenda. So first of all, dear candidate, I would like to congratulate you with a very nice presentation. I think it was a very didactic overview of your work. Also, the thesis manuscript itself, I think it was extremely well structured and very clearly written. And so I really enjoyed reading it. Until I actually came on page 2, where in section 1.2, you made a statement on the definition of the Qst S2 interval. So Q from the QRS complex of the electrical activation, S2 being the sound associated to aortic valve closure, where you state that it is the period from electrical activation till the end of ventricular mechanical contraction. And so I was wondering whether that statement is fully true, and whether you indeed consider the mechanical contraction completely finished when the aortic valve closes, and how that might relate to observations we have made on post-systolic shortening in ventricles.
Esteemed opponent, thank you very much for your question. Regarding the QS2, yes, I did say that QS2 is the interval from the electrical activation to the end of the mechanical contraction. And of course, there are a few confounding factors, as I just explained a little bit. Yes, but I think QS2 is very close. It's very close to the from the electrical activation to mechanical to the end of mechanical contraction of the ventricles. Of course, we can perform a further study in order to test the correlation, especially when we try to measure that using the ultrasound and so on. Yes.
So maybe another way of looking at it or posing the question is you made the analog with the runners that get started after the starting shot. Of course, this is true if you look at the individual level, and so if one runner needs to end before the other one. But in the heart, all segments are supposed to work synchronously towards a collective goal, which is pushing out the blood collectively. And so maybe the aortic valve closure is more related to the collective response rather than the individual response. And so maybe in that sense, it's a bit whether you look at the segmental contraction or relaxations or the global ones.
Would you agree with that? Or? Yeah, yes, and actually I agree with that. And for S2, it is simply driven by the pressure difference. So actually, I think there is no way for us to relate this with the abnormal segmental contraction or relaxation of the heart. Because heart sounds are more about global function of the heart. It is not about the different segments of the myocardium. Yeah.
Right. So the intraventricular delays are maybe not captured by it. A second question I have is related to sampling frequency and frequency content of the phonocardiographic signals. Because if I looked over the different chapters, I noticed that in chapter 2, you used an accelerometer studying the S2 splitting, where you bandpass filtered the signals between 50 and 250 Hertz. In chapter 3, you used another device from Medtronic in this SORC study, where you sampled at, if I read correctly, 128 Hertz, implying to me that you assume the highest frequency component is 64 Hertz, according to the Nyquist theorem. And then in chapter 4, when you used the digital stethoscope, you sampled at 500 Hertz, and the filtering was done up to 200 Hertz, if I remember correctly. So I noticed that in different studies, you use different sampling frequencies, different bandpass filters. And in the end, I was wondering if you now have a phonocardiogram, yeah, how should it be sampled and how would it be filtered to extract certain features?
Thank you very much for your question. Actually, because we use multiple devices to record heart sounds in our research, we can kind of say that our results are generalizable to some extent to these devices. That is a good thing. But if we look at time frequency of the heart sounds, most energies are located in the frequency range below 150 Hertz. You just mentioned about the ideal machine to record heart sounds. So I think if you want to save the power of recording heart sounds, maybe you can set the sample rate to 500 Hertz minimum, because in this case you can reach the frequency of up to 250 Hertz. That is maybe enough for the normal heart sounds for S1 and S2, but may not be for murmurs, because murmurs have higher frequencies. So in this case, I will say that 100 Hertz of sample rate may be better. Yes, that's my answer.
And the 128 Hertz sampling of the Medtronic device, is that then adequate if we go up to 150 frequency content?
Yes, the low sample rate of Medtronic's device did cause some problems. For example, as you can see, the standard deviation of the measurement of the systolic intervals was quite large. That is because of the low sample rate, so that the standard deviation may become larger. Yes. But for our analysis of the timing of the heart sounds, it's because we take a few heartbeats and use the mean value, so the trend may not change, and we use the trend to optimize the CRT.
Okay, thank you. I had some more questions, but in the sake of time, I'll leave it with this, and I'll give the word back to the project.
Thank you very much. Very well appreciated. The opposition will be continued by Professor Bruno Larocca. He's affiliated with the Department of Clinical Heart Failures at our university, and I'd like to give him the word.
Thank you very much. Dear candidate, of course, first of all, I also would like to congratulate you and your team for this nice work. And actually, I would like to continue with, what you are going to do in the future. You said you would invest in Mhealth. Yeah. And you also, in your chapter 5, you said that this can be clinically used and implemented you don't really say how and what actually can be done. So this is the first part, but then I also would like to ask you, well, how or what are the next steps to proceed with that?
Yeah, no, highly still important. Thank you for your kind words and your question. Yes, so nowadays if you look at the literatures, actually there are some real challenges facing ahead. The first one is whether Mhealth can really improve the outcomes of the patients. Because if you look at some remote monitoring studies using like the pulmonary artery pressure monitoring and so on, actually the technique did not seem to reduce the mortality or hospitalization that much. But of course it worked. The results were diverse in different studies. And that is also the case for heart sounds. So far we did not see a very clear study which shown that digital health of heart sounds does work to improve the outcomes of the patients. But for heart sounds, actually, as I shown in my presentation, it has a very long history of research. So we have very solid base of the knowledge that heart sounds are physiologically related and so on.
Yeah. But sorry to interrupt you, but I think as a first step, you actually should think about, well, where could it be used? I agree with you that, of course, in the end, you need outcome trials to really show that it's of clinical value. But I think the first step actually would be, to my opinion, that you think, well, where it could be used, and then to think about how you can proceed with that. So where do you think it could be used?
Yes. So in the hospital, we already have MRI and ECG and so on. So we think about this question, actually we need to think about what is unique for heart sounds. So for ECG, you can access the electrical activation of the heart, but there is no way for the ECG to access the valve closure or pressure difference or contractility of the heart. So because heart sounds, as I shown, is about contraction, relaxation, feeling, and also myocardial properties. So I think these are the aspects which can only be done by heart sounds or by ultrasound. But for ultrasound, of course, it cannot be done at home so far.
Yeah. But in what clinical setting? Because I agree with you with the physiology, but that doesn't translate in any clinical action or clinically meaningful circumstances. So where do you think it is promising?
And so for the first case, maybe for heart failure, the assessment of heart failure patients.
How?
Yes, and just as we did in the optimization of CRT, so these patients had heart failure, so we can access the cardiac function using the heart sounds. The second one may be for the post-operative follow-up of the patients with valvular diseases, such as the TAVI and so on, because for these patients, they may have short-term leakages of the valves. And thirdly, we may also use that for post-operative follow-up of the arrhythmias, such as for the AF. After the ablation, there's a quite high percentage of patients who have recurrence of the AF. So we can use that as a simple tool to follow up the patients.
Okay, and then you would listen to only the first and second heart sound, or also to murmurs? And do you have any information on that this is really feasible? Yes,
actually there are quite some studies showing the relation between S1 amplitude and the LVDB max. So LVDB max is a common indicator of myocardial contractility. Also, my colleagues, they use machine learning to show the relation to predict the blood pressure using heart sounds. So, of course, we have a model here. We have a model in our BME department and showing that for heart failure patients, the splitting amplitude of the heart sounds, they change in heart failure patients. So these can be the examples.
Okay. Yeah. Thank you. I would like to give the word back to the prorector. Thank you.
Thank you very much. The opposition will be continued by Dr. Lins. He is affiliated as cardiologist at our university, our hospital, and I'd like to give him also the word.
Yeah, thank you, Prorector, and yeah, thank you, candidate, also for presenting your data, and congratulations to you and the complete team to put this together. So I would actually continue a little bit the discussion which was just started by the opponent just before me. So imagine, so I'm in an outpatient clinic. I have my patients in my outpatient clinic. You are coming around with the support by Professor Lumens of $250,000. You actually developed a little bit your app further. And now you want to sell this to me as a clinician. The thing is, so I would understand I can actually use this in patients. The first thing is, of course, what I would see, age seems to be a problem. So how do you want to fix this problem with age? Is this improving the technology? Is this excluding older patients? Or what is the approach there?
Esteemed opponent, thank you very much for your question. Regarding the use of the device in the outpatient clinic, and also regarding the confounding factor like age, I think if I want to persuade you, the first point may be that if you forget to take your stethoscope, which is always the case in the hospital, you can use this one and put that on the chest of the patients, and you put the headphones to the ears, and then you can listen to the heart sounds. So that is one of the application.
I understood this, but if I have now an older patient in my outpatient clinic, should I exclude him and not onboard him with this app, or do you think that the technology needs to be better, the app needs to be better? So how can I get my older patient to this app?
Yes, actually for a lot of patients with heart diseases, they have a quite old age. So I don't think you should exclude these patients. It is just the problem of how we can improve the app so that the users can more easily use the app. So I think one of the easiest solution is that we ask the users to put their phone on the chest, and then using earpieces, so users can listen to the heart sounds. And then we ask the users to search for the best position of listening to the heart sounds. So that, and then I think the reproducibility of this way is quite high, because each time the users will just try to search the position with the loudest heart sounds. I think this solution is regardless of age, because for young boys or young kids, they also can search for the best location for detecting heart sounds.
Yeah, so really integrating then actually the patient in providing feedback where to place it best. Okay. Yeah, that's convincing. So then the next thing, so then I have, for example, 20 patients in my outpatient clinic. All of them are collecting data, but not all data is actionable, what also was already mentioned just before. So do you think that there are specific thresholds for those recorded measures which should result in action? So give me just a threshold of, for example, one of your measurements where I, as a cardiologist, should call the patient, get the patient into the hospital, or do you think we are not there yet?
Yes, I think we should implement some kind of quality control into these heart sound recordings. Sorry. Actually, in the chapter about the smartphone, we try to classify the quality of heart sounds into good, uncertain, and bad quality just by visually looking at the signals, whether S1 and S2 exist. I think we can continue to improve the algorithm so that the algorithm may be able to automatically identify the quality of the recordings just in real time, so that so that if the recording is not good, you can maybe change the position and to make a new recording again.
This would be the quality, but still I wouldn't have a threshold when I should call so a good recording should not activate me to call the patient, right?
Yeah.
So I need a threshold where I should do something or not do something. Do you think that this will be ever possible just based on one recording, or is this a change over time, relative change compared to other recordings, for example?
Yes, and of course you can ask the patients to daily measure the heart sound so that you can observe the trends. And then if you can see the changes, and then you can set a threshold so that the doctors can be informed about the changes of the patients. But I would say that is something that we do not have evidence yet.
Yeah.
Yeah. we can set a threshold, of course, yeah.
Okay, thank you very much. I would like to give the word back to the prorector.
Then the opposition will be continued by Dr. Bruining. He is affiliated with the Department of Digital Cardiology at the Erasmus University in Rotterdam. And of course, I have to thank him on behalf of our university that he joins us today live here from Rotterdam. Thank you.
Thank you very much, Mr. Rector, and it is a great pleasure being here. So, dear candidate, my compliments to you, your promoters and co-promoters for this very interesting topic you investigated. And I'm also very pleased that I, as Editor-in-Chief of the European Heart Journal Digital Health, received your work to our journal. Now, can one of your paranyms read out loud proposition number 4?
The ability to record heart sounds with a smartphone provides a unique opportunity for simple and cheap out-of-hospital checkups of patients.
Thank you. So I would like to focus on the cheap out-of-hospital checkups on patients. I don't know if you followed the news last week or the week before about the new iPhone 14, but it starts with 1,000 euros. And if you look at bol.com, you can buy a stethoscope for 100 euros. So I think this proposition is difficult to defend, and I would like to help you a little bit. So I have a suggestion to rephrase this in the following. The smartphone, a device that most people carry with them at all times, can also be used as a stethoscope, providing valuable diagnostic information during remote consultations. What do you think and why?
Yeah, esteemed opponent, thank you very much for your question. I wouldn't argue that iPhone is more expensive than this phone. This phone is only 100 euros, so it's much cheaper than a digital stethoscope. So as for the price, it varies by countries. We should also think about the more countries which are less developed in this world. So, but let's go back to the using of this app for the consultation of the disease consultation. And I think still we need some evidence to show that. That is something that we need to do. But I think, as I said, the heart sounds have a long history, so we have a very solid base. But for the cost effectiveness of this study and also benefits of the app, yeah, that's something we need to investigate. No, I don't think I have a very clear answer to this.
So you still stay with your proposition as it is now? Is I understood. Okay. I have another question. In chapter 5, I think, chapter 3, you have a sentence where you say that the human ears and brains are actually not good enough to, yeah?
No.
What do you want to say? No.
Yeah, so I don't think human ears and brains are good enough if we compare that with the digital stethoscope, because the first thing is, can you still remember the heart sounds that I played at the very beginning? I don't think so. So first, for human brains, they cannot exactly recall every details, and also because our ears serve as the filter, so we are more sensitive to the higher frequency of the sounds rather than heart sounds, because heart sounds, the frequency is below 100 hertz. So most energies have quite low frequencies, which cannot easily be detected by the doctors, even in hospital. So that's why in hospital, if you use a stethoscope, the doctors will require all the others to keep quiet in order to listen to the heart sounds.
So the use of the brains is related to the, let's say, the sound analysis.
Yeah.
But in chapter 5, you still use the brains to the visualized sounds.
No, seeing is believing, not listening is believing. So if we look at the PCG, we can observe the details, but using ears, we cannot differentiate between like 1 millisecond from the other milliseconds, because for human ears, it's also a sensor. The sample rate is also quite low if you compare this with the PCG.
Right. If I look in the literature, I digged in a little bit and look to the spectrums of valvular diseases, then I could easily interpret that as some kind of noise. So how can you differentiate then with an automatic algorithm that it is really paravalvular leakage or something like that?
Yeah, and for the noises, in general, they have higher frequencies. And so, for example, if we collect the heart sounds and the patients are talking, we can see that the frequencies go up. And then we can develop an index to automatically assess the quality of heart sounds in this way. Of course, the real line may be more complex. The patients may also be breathing, and the breathing sounds also have higher frequencies compared with heart sounds.
Okay. Well, thank you for your time, and Mr. Rector, I give the floor back to you.
Thank you very much. We are well in time. The opposition will be continued by Professor Vernooy. He is affiliated with the Department of Cardiology, Electric Treatment of Heart Failures at our university, and I'd like to give him the word.
Thank you, Mr. Pro-Rector. First of all, I really would like to congratulate with this marvelous thesis. Really great work, especially considering your background as a medical doctor and then making such a technical thesis. My compliments. Even in our monthly meetings, I sometimes had problems following you with all the technical analysis you showed during the meeting. So really congratulations. And with that, of course, your promotion team. I have a couple of questions. And first of all, I got intrigued by one of your propositions. And I don't know whether Latin is also taught in China, but maybe you could read me, or one of your paranym, read me proposition 10 and tell me the relation to this thesis.
Ask the other paranym as well. Woody? Whatever you want. It's your choice. Okay.
Yeah, it's quite challenging for me, this one. It's a non-sort multi-precandle enter scene necessitated. Yeah, thanks.
Thank you very much. Yes, so for your questions, actually the sentence is in Latin, so if you translate that into English, is less is more. Or if it is not necessary, you do not need to add details. So that is actually the style of how I do research or how I write the sentences in this thesis. I would like to try to keep my sentences as simple as possible, and then try to squeeze the information a little bit rather than write a lot of things.
Okay.
And it's just the style of writing and research.
But then with CRT, which is your focus on, we have seen in literature like hundreds of measurements that tell us about desynchrony measures, tell us about LV function measures, and now I see a lot more measurements coming up. In chapter 2, you very nicely showed the splitting of S2 in relation to the desynchrony, very much the desynchrony of relaxation, I think. And then in chapter 3, which I really like, is then you measure the VS1, the S1, S2 interval. You start in chapter 3 with a model of complete AV block in the animals. But then suddenly you take, in the patients, you take a different model. And actually I was wondering can you explain me why you also incorporated the S2 splitting also in chapter 3? Because you have a different model in the patients. Can you maybe elaborate on what the results would show us if we would have taken the S2 splitting in chapter 3? Yeah,
highly important. Thank you very much for your question. So the reason why I did not implement the S2 splitting algorithm in the systolic time interval in the patients is because of the low sample rate of the sensor in the soccer study. The sample rate is 128 hertz. So the highest frequency that I can reach is 64 hertz. But my start algorithm in chapter 2 works for the frequency range from 50 hertz to 250 hertz. So it is higher than the sensor can capture. So that is one reason. And imagine that if we had the sensor of higher sample rate, let's say 100 hertz in the study, I will run the algorithms and then use it for CRT optimization. And then for the patients with LBBB, maybe we will be able to see reverse splitting. Because as you can see in chapter 2, we did not see reverse splitting because in pigs, the conduction velocity of electricity is much faster. But in humans, for LBBB, we may be able to see the reverse splitting, and then as we try to resynchronize the two ventricles, the P2 may occur later, and then A2 occurs earlier, so which means normal conditions.
Okay.
Yes.
Very good. A question then related to that, because you used all different methods of looking at of measuring heart sounds. You can do it endocardially, you can do it epicardially, you can use it subcutaneously in the device, or you can do it on the skin, like with the iPhone. So the very measurements. Now there's of course one company who uses it already, and you spoke that already about the sonar lead for Soren. Let's presume now that you were hired by Soren, and that you could advise them what to measure, because actually in the sonar system they don't use these kind of measures. They use like an amplitude measure, am I correct? And they use then a half-wave value between the two extremes. If you would be in charge of Soren, what would you advise them to start using to optimize the CRT system?
Yep. Actually, for sonar sensors, for the company, they had the trial published in European Heart Journal already. That is the Respond CRT trial, which they saw that they can use the S1 amplitude and correlate that to myocardial contractility. But I think that is not enough. As I saw in my thesis, they can also use the S2 splitting. So far, we don't know what is the relationship between S2 splitting and outcomes of the patients. If you consider that heart sound has a very long history, that is something really amazing or surprising. And also regarding the relation, regarding the relation between the systolic time intervals and outcomes of the patients, we have a few studies, but that is not enough. But for the HEPAF chapter in my thesis, actually, still we don't know how heart sound frequencies are changed in the patients with HEPAF. So if I were the manager, I would advise them to study more HEPAF, maybe.
Study more HEPAF, but it's a HEF-REF population.
Yeah, sorry.
This time with the CRT patients, of course.
Yeah, for HEF-REF, as I mentioned, the splitting is something that we don't know yet. But I think it is very important if you think about the CRT.
Okay, so
Yeah.
you would go for splitting.
Yeah, go for splitting.
Okay, and regarding that, because you looked at the splitting, and what really struck me is that actually the value, when you programmed an AV delay of 150 for both RV and LV, that was actually rather low in the figure, more close to RV pre-excitation rather than LV pre-excitation, where you would think when you have minimal splitting, it would be halfway between RV and LV pre-excitation, halfway. There's an optimal synchrony. So it seems like the splitting is not correlated to really electrical resynchronization, or am I incorrect?
No, so actually I discussed this question also with some experts in the field. So there was one paper published by Luke Hackman and also Cora in Czech Republic, so that they use ultra high frequency ECG in the patients with the RV apex pacing, which was the method that we used in our animal experiments. But what they found was quite surprising, because they found that if you use RV apex pacing, actually, in some patients, the electrical impulses pass the apex into the left side, so that the two ventricles do not, the two ventricles are not necessarily desynchronous that much, because the propagation of the waveform has changed.
Or could it be that the endocardial spread of activation from right side is faster than the epicardial LV activation? I'm very happy with your answers and would like to give the word back to the prorector.
Thank you very much. Then the opposition will be continued by Professor Schotte. He's affiliated with the Department of Cardiac Electrophysiology at Maastricht University, and I would like to give him also a chance to have some discussions with you. Professor.
Thank you very much, Mr. Prorector. Dear candidate, also from my side, congratulations, very nice thesis. I read it with great interest, and my congratulations also go to your promotion team, of course, and also to your family. So for the discussion, I would like to go to chapter number 4. That's the chapter where you investigate the association between phonocardiographic parameters and echocardiographic parameters in patients with diastolic dysfunction. And my first question is about the fast Fourier transformation you use in order to determine the frequency content of the heart sounds. For instance, if you and an example is shown on page 79. What I understand from the text and from this figure is that you use a low-passed filtered signal, 200 Hertz, and you use a 60 millisecond segment in order to perform the fast Fourier transformation. And what I learned from this kind of frequency domain analysis is that you have to be careful with the duration of this segment, because it becomes pretty robust when it is relatively long, and it becomes less robust when you make it very short. So if you look at this example on page number 79, you see that you only have a very few oscillations based on which you perform the fast Fourier transformation. And there is another problem here, and that is the fact that the frequency of this oscillation obviously changes. The amplitude goes down, it starts high and the amplitude goes down, but also the frequency goes down. If you look at the wavelength you see there, the distance in time between the minima, that becomes longer. So my question is, how robust was your fast Fourier transformation, and how much difference did you see from beat to beat?
Highly esteemed opponent, thank you very much for your question. So this question is about the FFT that I implement in the study. I agree with you that the choice of the window size is very important. As you said, if the window size is longer, we can focus on more low-frequency components of hard sounds. If this window size is smaller, we can focus on higher frequency. But we think that 60 millisecond segment is enough in our study. Because with 60 milliseconds of the segment, you can have the frequency of down to 15 hertz, something like that. And
yes, of course, but still, particularly when you have different frequencies in your signal, you run the risk that you do not have a clearly defined dominant frequency. You could also have used simple time domain parameters. For instance, you could determine the maxima and the minima and simply measure the difference in time between them. Did you consider to do that? It might be more robust in a situation where you have a very diverse frequency content.
Yeah, thank you very much for your question. I agree that imposing different frequency bands to filter the signal may change the result a little bit. But since in our study we implement the same procedures for all the patients, we try to correlate the frequency content with the EOE prime. We don't think that the filtering procedure matters that much. But because we implement the same procedure for all the patients, and if there is any bias, for example, the shifting of the signal in time, that will be the same for all the patients. And in the future, we are going to use the same filter also for the other patients. So if we can prove that this filtering method works, and then it can be applied for the other studies.
All right. Okay.
Yeah.
No, I understand this argument. Okay.
Yeah.
Now let's talk about the score, the phonocardiographic score, which you suggest in order to identify those patients who have an E over E prime of more than 9. And the performance of this score is shown on page 88, figure 4, left panel. And there you see that this score has a pretty good performance with an area under the curve of 0.85. So this is pretty good. But this number comes from your discovery cohort, so the matched patients, 25 patients. Yeah. And when you then add all the other patients that you could not match in your matching procedure, then the area under the curve goes down to 0.74, which is a lot. I understand it's not statistically significant, but this has to do with the relative low number of patients, of course. But is that not a worrying drop in performance? So if you would perform a validation study in a completely independent cohort, do you expect that your score would still work?
Thank you very much for your question. So we did think that there are some risks in this score. So we are going to delete this from our final publication. But for your question, the drop of the AUC from for example, from 0.85 to 0.74, that is because of the representative representativeness of our cohort. Since the sample size of our study was quite small, imagine that if we perform a larger scale study and the sample size is much larger, and the patients are more representative of the general population. In this case, I think this method will work in developing a score. So the reason why I put the figure here is partly because we would like to validate the methods.
I think you finalized the answer, or would you like to add something to the answer to Professor Schotte?
I think I already finalized the answer.
Okay. Exactly.
Thank you.
The time appointed for defending your thesis has now passed. The degree committee will now withdraw to discuss not so much the quality of your thesis, but in particular the way you have defended your thesis this morning. I request that you and your company await the results of our deliberations and return to this room. Thank you.
Thank you. So that's why I asked you to read it. That is Latin.
It's Latin.
The PhD defense has now ended. The degree committee will debate the candidate's performance behind closed doors. This process usually takes about 10 minutes. In the meantime, let's take a closer look at Maastricht University's renowned teaching method, problem-based learning. Once the pro-rector reconvenes the session, we'll tune in and continue the live stream.
Problem-based learning, or PBL. What does that mean exactly? 3 of my fellow students and I will show you around. Every week, we analyze a different case or issue together. We discuss the case and everyone can contribute different perspectives to the group discussion. If we get stuck, our tutor helps us out and suggests what we could do next. I prefer going to the library to prepare. Here, I can focus and I have quick access to books or journals that help me understand the case. Today, I can also train my stitching skills in the Skills Lab, where you can immediately put into practice what you've learned. After a day like this, I like going to the gym to clear my head and get ready for the next day.
At UM, you meet people from all around the world. Hello guys. Some of them are doing their exchange semester here, and they often say that PBL helps them learn and retain things very easily. I can understand why. It's a very active way of learning because you have to bring your own perspective to real-life cases. You have a lot of freedom to manage your time, your studies, your hobbies, and your work. Of course, that also means a lot of responsibility. Right now, for example, I'm arranging my exchange semester in Madrid. How cool is that? In this group session, we're the managers who have to allocate the resources of a real company. This is how we put into practice what we learned this morning. Studying here means being proactive and learning to plan well. Prioritizing and performing well under stress are great skills that help you develop as a person. But now, it's time to grab a coffee at the Student Service Center.
Right now, we're at the Brightlands Camelot campus. Here we can apply knowledge from lectures and tutorials in a practical setting. This helps us understand what we have learned and further develop our lab skills. Today, we're determining the amounts of cholesterol in various products. What I really like is the project periods at the end of each semester, where we complete a full research project that includes planning, collecting data, analyzing, and presenting the findings. That way we learn how research works and we're able to see what it's like to be a real scientist. After practicals, I have to write a lab report that also helps me process everything I have learned today. UM has a lot of learning spaces where you can work on your own or with other students. This evening, I'm meeting my friends for a movie night organized by the MSP Study Association.
If you study law, you have to read quite a lot. Not all information is relevant, so you learn how to easily find the information you need to solve your case. In the afternoon, I have to give a presentation, so I like to practice it with a fellow student. Later today, a lawyer is giving a lecture. This will help us better understand the case we're working on. Speaking in front of a group is quite exciting the first time round, but you get too used to it quickly. And having to present helps you also to adopt knowledge better. What I like the most is that we sometimes get to enter a plea in front of a real judge. These moot courts are really exciting. Now it's time for drinks with friends. Studying is important, but so is relaxing once in a while.
Dear Mr. Luo, the degree committee here present has assessed the quality of your thesis, but also the way you have defended your thesis this morning. Yes? In view of its positive verdict and taking into account your previous qualifications, the degree committee has decided to grant you officially the degree of doctor. And I'm looking to your face, you appreciate it. Professor Prinsen is authorized to confer upon you this academic distinction in accordance with Dutch university customs, and therefore I invite your supervisor to take the floor.
Please all rise.
Do you promise to work in accordance with the principles of scientific integrity at all times, to be careful and honest, transparent, independent and responsible?
Yes, I promise.
By the authority vested in us by law and in conformity with the decision of the committee here present, I hereby confer upon you, Hongxing Luo, the degree of doctor and grant you all the rights attached by custom and law. As evidence of this, I now present you with the degree certificate signed by the rector, secretary and other members of the committee and affixed with the official seal of the university.
The photographer may proceed if they want. Okay.
Dear Dr. Luo, dear Hongxing, congratulations with the achievement of your PhD diploma. As already mentioned by the assessment committee and members of the Corona, you wrote a beautiful thesis and had a good defense. You clearly showed that you have become an independent researcher. I also like to congratulate your wife, Yongchan, and your family who attend online. You all can be very proud of him. Our journey started 4 years ago. We in Maastricht became partner of a European international training network called Personalized in Silico Cardiology, abbreviated PIC, with principal investigator Professor Pablo Lamata from King's College in London, a consortium of 8 universities and 2 companies. One of the obligations of such a network is that only foreigners can be appointed as fellow. In Maastricht, we had 3 fellow positions to fill in. And in that group, we already had Philip Westphal as a technical guy, Medat Shah Mohammadi, the one doing computer modeling, and I needed a fellow with biomedical background. For this, I saw the application of someone from China. What already was remarkable in his CV was that he had already several publications in the international literature, with topics like 3D printing applications for the heart. And also in other regards, a very special CV for a master student. I organized an interview by Skype. Zoom wasn't available yet. And what was immediately struck me was the perfect English you spoke, which indicated to me that the published papers were not only written by your supervisors, but certainly also by you. Moreover, you had already looked me up on PubMed and knew much about resynchronization therapy, the topic of the thesis. Clearly, you were the ideal candidate. You started the appointment here in July 2018, immediately visiting a workshop organized by the PIC consortium. The goal of our research in Maastricht was to investigate the potential of mechanosensors for assessing cardiac function. The first year of the project was dedicated to the animal experiments, where you collaborated with Philip Westphal, who built new sensors and a new acquisition system. With your experience in cardiology, you were the ideal person to also work with biotechnician Marion Kuiper to do complicated animal experiments. So far, this work has resulted in 3 publications, 2 of which are in your thesis. During the data analysis, you already showed a considerable amount of independency and originality. The START algorithm described in chapter 2 was entirely your idea. Doing so, you showed that splitting of the second heart sound can be used to assess ventricular dysynchrony. While finalizing this paper, you went to China for a Christmas holiday, 2019. At that time, a strange new virus spread quickly, taking many lives and scaring both the people and government in China. Hospitals were overflowing, but also their protection was so poor that people were scared to go to the hospital. You felt immediately the urgency to do something and developed a 10-question online questionnaire with a few simple questions, helping people to know whether they should go to the doctor or just stay at home. After launching that app in China, there were more than 18,000 responses giving you information on the prevalence of the fever in the various regions of China and its development over time before and during the first lockdown. January 2020, so before COVID was even known in Europe. This work, together with your wife, was your first step into Mhealth. It's now as an appendix in the thesis, but clearly showed your motivation to continue in that direction. For your real thesis work, you continued with the analysis of data from a clinical study already performed by Medtronic, where heart sounds were collected using a microphone in the pacemaker. This study extended your analysis of the animal experiments, showing that heart sounds can be used to steer the programming of pacemakers, even when the sounds are collected outside the heart. And then you came up with the idea that heart sounds might be useful to diagnose heart failure, in particular in patients with stiff hearts. Using a small digital stethoscope, you managed to collect data with the help of Jeremy Weerts and Vanessa van Empel, and showing that indeed advanced analysis of heart sounds may be useful in this respect. And working on that project, you meanwhile discovered that heart sounds can be measured using the microphone of a smartphone. We now know that you were not the first one to do this, but there are still very few publications on this potentially quite useful possibility. In discussing how to expand this, you took the initiative to talk to Pablo Lamata, and he found financial support that allowed to hire a company, Salul, to build the app using your analysis techniques. Like the Chinese questionnaire, this app gave thousands of responses with minimal advertisement, providing a large number of heart sounds from ordinary people, indeed pointing to the ultimate potential to use the smartphone for home monitoring. I think I sketched how diverse your work has been and also the many original thoughts you had. Actually, you had many more, but at some point I had to stop you in order to let you finish your thesis. But I find asking such constraint to a PhD student a luxury problem. The same holds for the many discussions about your new ideas and what you wanted to publish. You are extremely motivated, enthusiastic, and ambitious to deliver good work and also towards the future. You wrote already a few applications for financial support for future studies, so thank you, Joost Lumens, for providing the $250,000 already, so we can go to the future. So far, your real applications were not successful, but most recently, you applied for a grant from the Maastricht China Collaboration Network, which may be more successful. Your drive is also shown by how you continue. As of next week, you start a postdocship in Oslo with my good colleague Espen Remme, while still keeping a part-time appointment in Maastricht. Finally, the audience may have noted that I mentioned the COVID pandemic as the source of one of your publications. Many PhD students use, rightfully or not, COVID as an excuse for a delay in finalizing the PhD. However, you took benefit of it with the already mentioned article. Moreover, you were also capable of maintaining good communication with me by Zoom, while you behaved like a real Chinese to be very strict in keeping the isolation, avoiding infection. So there are really very few obstacles that can keep you away from success. You are looking for a future in Western Europe, independent of whether this will be in academia, industry, or startup company. I am sure you will reach your goal. And with that, I wish you all the success and also a very happy family life. Thank you.
Thank you very much.
Well, thank you, Dr. Luo. And I would like to be the first one who can call you and officially give that name, Dr. Luo. And also on behalf of Maastricht University, I would like to send you my congratulations. You did a great presentation and a good defense. In my congratulations, I also go to your wife who's sitting here. Also congratulations, yes. And of course to the promotion team who guided you over these years to bring you to the results here. I also like to thank the members of the Corona who took time to read your thesis and to prepare questionings for a 6 minutes frame. And I think everybody has a special position. I also thank in particularly the members from outside. Well, Professor De Hoge has already left for another meeting, but I'm said to Professor Bruining from Nijmegen, thank you again for joining us. A special address is to your other Chinese students who are sitting here in the audience. And I see there are quite a lot of Chinese students here. For those who are going to defend, we're looking forward also to your defenses as well. And you have a good example seen today, how we like to see it.
Don't put them into too much stress.
Yeah. And by that, I'm going to close this session officially, use my hammer. And we're going to proceed as follows. The members of the Corona here, together with the new young doctor, the gyros and some pie. I'm not sure what's available. And you don't have to wait for us, but you can go straight to the rafter. Thank you very much.